Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. Welcome back to the biotechnological slot with me. So today we are gonna look at enzyme catalytic process. Okay, so before we go into the topic for today, let us summarize a little bit. So for the past 2 weeks, we have looked at enzymes, what they are. We've looked at of course, the first week we looked at introduction to biotechnology, what is biotechnology and the principle behind it, or definition. We've looked at also some examples of utilization of biotechnology in chemistry. And then the week after that, we've looked at enzymes. What are enzymes? How do they work? The principle behind the models behind enzymatic work. For example, the lock and key model, and also the induced fit model. Okay, and we also looked at the kinetics, Maclaurin equation, if you recall. Okay, so on how to derive the equation, and what are the principles behind the utilization of the Maclaurin equations. We also looked at the equilibrium expression of the enzymatic reaction, so that towards the end of the day you can actually derive the enzymatic kinetics. Okay, so those are very basic things. So today we're going to look at the catalytic process itself. Okay, some of the factors that influences the catalytic process. Well, basically we're looking at more on a micro molecular level. Okay, so let's get started. Okay, so what are the driving forces? So when we talk about enzymatic and enzymatic reaction or biocatalytic reaction, we should know what are the driving forces, what pushes this reaction forward. Because as a chemist, we always remember when we draw an energy diagram. So say for example, an energy diagram without catalyst should go somewhere like that, okay, which is very high. And then when you have an enzyme, so the starting point and the end point is always the same. So what makes it different is the activation energy of the reaction itself. So with an enzyme, if I may change my color, okay, with an enzyme you definitely will have something like this, because otherwise there's no point of using an enzyme. Okay, so as you see, the activation energy is now less. Okay, so that is the energy difference of the reactant and the products, and this is the activation energy between a reaction with enzyme and a reaction without an enzyme. So as you can see, it's very critical for you sometimes to introduce an enzyme for your reaction. Okay, so moving on. So what are the driving forces behind this enzymatic activity? Okay, so the structure of an enzyme is influenced by enzyme stability and sensitivity. Yes, of course. Okay, so as we looked at the model of lock and key or induced fit, we actually see that the structural integrity or structural movement of the enzyme is part of what makes the enzymatic reaction works. Okay, so well, of course there are a few theories, but what we focus on was the lock and key model, okay, which is talking about enzyme and substrate specificity. So you need to have like a very high specificity for the biocatalytic reaction to work. And the second one is the induced fit, whereby the enzyme are actually not static, but it's more dynamic. The geometry of the enzyme is not fixed, and when you have a substrate coming in, so the enzyme kind of like changing its geometric phase to fit into the substrate, so that it can push the catalytic reaction forward. So we know that the structure of the enzyme are influenced by the enzymatic stability, and so sensitivity in terms of the sensitivity to the substrate, okay, and the stability of the enzyme itself. because if you denature the enzyme, it will no longer work. So the structural integrity is very important. Okay, so there are two main factors that can influence the structure of an enzyme. So the first one, well, there are a few, but what we're going to focus on is these two things in a little bit more detail. The first one is a chemical influence. Okay, so chemical influence, meaning water solvation. I already touched a little bit on structure of water. Okay, from the previous lectures. We might also look at a little bit in the future about how water molecules are influenced in the structure of the shape, the structure of on how the proteins and the substrate when they move in to match one another, what happened to the water, the structure of water. Okay, in terms of chemical also, there are influences of pH, change of pH. Of course, as a chemist, when you do analytical chemistry, you do a lot of pH experiments, right? So you drop in either acid or base, sodium chloride or sodium hydroxide, and change the pH of the reaction. And when we are talking about chemistry, when you learn about chemistry before this without the biological component, what you're talking about, or what you're looking for, is basically acid or a base catalytic reaction. So as simple as that. So either you have an OH or you have an H plus, OH minus and H plus, that can influence your reaction. Okay, for example, the simplest reaction that you looked at is ester formation. Okay, where you have a COH group and an alcohol group. In the presence of acid catalysis reaction, you'll form an ester. Okay, so that's the simplest basic reaction. But when you have an enzyme, so enzyme works at a certain pH range, the structural integrity of the enzyme is influenced by pH. We'll look at it in more detail in the next few slides. And also ion concentration. Okay, so some enzymes are influenced by the ions surrounding it, either a metal ion or a sodium ion, and so on and so forth, a chloride ion. So either an ion or cation, of course. So we might also look at it in more detail. Time that I spent to talk to you guys about this. All right. So, and also temperature. Okay. So when we talk about temperature, we do know that thermal energy influences influences reaction, regardless of whether it's a biological reaction like using an enzymes, or a normal reaction that you do in the lab. So sometimes you do need to control the reaction. Remember, when you do your organic 1, organic 2 reaction, sometimes you need to heat up. Okay, you need to heat up a reaction, a test tube, for example. When you do I can't remember the name of the reaction, but when you do a reaction, sometimes you heat it up. Okay, sometimes you cool it down. So depending on what you want to achieve, depending on the specificity of the reaction itself, so you might need to change the temperature. Similarly for enzymes, so some enzymes work at a certain temperature. Okay, but because enzymes are from biological entity, so you took it out from an organism, so the temperature is dependent on where the enzyme is sourced from. Okay, so for example, if the enzyme is sourced from humans like us, the optimal temperature is normally around 37 degrees. Okay, so but there are enzymes that are working at a higher temperature. For example, when we are talking about COVID-19, when we're talking about PCR, okay, you heard a lot of PCR. Tan Sri, Dr. Nur Hisham always talks about PCR this, PCR that for COVID-19. So PCR actually uses enzymes. Okay, well, the old technology, the newer technology, some of them might use it, some might not, but in general principle, PCR uses enzymes, and the enzyme is not from a human source. Okay, so a PCR enzyme comes from a bacteria that lives underneath the ocean floor, near what do you call it, it's kind of like a hot spring, so where the hot water from the earth core, so I left this for so long I just remember it a little bit. The bacteria is actually living underneath a flow bed, whereby you might have like kind of like a volcano activity, but it's not a volcano, it's more like a hot water springs. So the bacteria lives at a very hot temperature. If I'm not mistaken, it's around 80 or 70 degrees. So that's why when you do a PCR, if you learn about PCR, the system actually works at a high temperature, because at high temperature this enzyme actually producing its catalytic reaction. Okay, so those are the two things that we gonna look at in a little bit more detail: the temperature dependent structural enzyme, and the chemical influence of chemical influence on the structure of an enzyme. Okay, so when we're talking about these two factors, it's not just simply a chemical and temperature, of course. So there are a lot of major factors that comes into play and that influences either chemical or temperature, or both simultaneously. Okay, so what you need to know is that unnatural change in structure, it can be a catalytic process, but it might also be a non-catalytic process. Okay, depending on the situation. All right, so changes in structure, when we were talking about the induced fit model, yes, it's a catalytic process. But change in structure, when we are talking about denaturation, whereby the enzyme is no longer in the shape that it should be, then it's kind of like killing off the catalytic process. Okay, so to look at these changes in a little bit more detail, it's very critical for us to actually know what are the chemical process involved in the stability of the enzyme and in the interaction, and thereafter understand the influence of the basic structure and its influence on the basic structure of an enzyme. Okay, so we looked at in this principle, so most enzymes are globular enzymes. So when you see my hands doing this and this, so it's kind of like shaping the enzyme into a ball shape, a globular shape. Okay, so most enzymes are globular, so most of enzymes fold in a certain way that it forms kind of like a ball shape, not really a solid sphere, but a ball like shape. Okay, if you recall, I forgot to put the picture here. As you recall, when we see the HRP horseradish peroxidase enzyme from the previous lecture, the structure is kind of like, you know, a ballish, right? So a ball where it divided into two, and you have the active site in the middle. Okay, so that's what we call as globular. We will look at it in more detail, not today, but probably next year or the week after. Okay, so but today we're going to look at in more detail about the primary structure of a protein, a secondary structure, a tertiary structure, and quaternary structure of a protein. Okay, for those who actually did a course with me last semester or last year, where we actually look at different structural levels of proteins, then for you guys it might be a little bit easier to understand what I'm talking about today. But those who did not sit for the same course, I'm not sure, I haven't looked at your names in very detail, you might need to read a little bit more, or ask your friends about these, you know, 4 features. And anyhow, this lecture is put on YouTube. You can find my other lectures related to these matters also uploaded from YouTube. It's a different course, it's a second year course. Okay, alright, so when we're talking about primary structure, we are looking at the amino acid sequence of the protein itself. Okay, so it's a single chain. So if you write it down, it will be like, you know, jotting down, say for example, alanine, 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 alanine. So a quad A followed by a lot more amino acids, and then that's it. Okay, so that is the basic structure. That's a primary structure. A secondary structure is where you are more focused on the alpha helices or beta sheet formation, and not to forget a random coil, whereby this primary structure fold on itself. Okay, so when you talk about primary structure, it's just a straight chain because you just write it down. You just write down all the sequences. Second structure is when the sequences are actually folding. So like for example, alanine is non-polar, it's more a little bit hydrophobic. If you have lysine, which is a more polar amino acid, so these interaction will fold the peptides, forming what you see and for example in the host release peroxidase enzyme structure. Okay, so that's secondary structure when we're just talking about the alpha helices, beta sheet, random coil, and so on and so forth, just the basic folding. And when you move to a tertiary level structure, we are now looking at in more a three-dimensional shape. Okay, not to say that secondary structure is not three-dimensional, it does, but the degree of a tertiary structure is bigger, so it folds in a bigger way. So, and also the main critical about a tertiary structure is that it comes from a singular primary structure. Okay, so one straight chain amino acid, so this side for example folds into alpha helices, the other side falls into a beta sheet. So when we're just talking about these two, alpha helices and beta sheet, they are the secondary structure. When these two are interacting with one another, forming a more globular-like protein, then we now consider it as a tertiary structure. Okay, so that's basic principle of tertiary structure. But when you have two of these primary sequences folding on itself, okay, and then interacting with one another, then you consider that as a quaternary structure. Okay, so a multiple subunit protein interacting for a certain function. We will see a little bit more example, some more fine examples, hopefully in the next few minutes. Okay, so influences. What are we will look at the factors that influences, or the driving forces that influences catalytic process. Okay, what we will look at today at least is the chemical forces. You probably learned about it in the first year, but if you forgot about it, we're going to touch about it in a little bit. We will look at the influences of pH. We look at the influences of temperature. We look at the influences of these forces. When I'm talking about the first forces, okay, we looked at the influences of these forces on the proteins or on the polypeptide structure. We'll go into a little bit more detail. So when I talk about the primary, secondary, tertiary, and quaternary, I'm just talking about how the structure works. We did not touch about what are the forces that causes all the folding and whatnot. We're going to touch about it in a little bit. We looked at substrate specificity in very tiny bit because we already touched about it. Basically, these involve the model enzyme substrate structure that we talked about, which is the lock and key model and the induced fit. Okay, so just a little bit. And finally, we will look at cofactors. What are cofactors or coenzymes? Okay, so those are two different things, but it can be interchangeable. I mean, for a chemist, you don't need to be very, very specific. Yes, knowing the specific is very good, but we're not going to talk about what are cofactors or how is cofactors different than coenzymes. Okay. All right. So let's move on to the first section, which is the driving factors. Of course, everybody knows about ionic interaction or Coulomb forces. Hopefully, you still remember. So, what are those? Ionic interaction are the opposite charges of polar charged amino acid. So, when we are talking about enzymes, when you're talking about the forces in an enzyme, about ionic forces in an enzyme, we always talk about the opposite charge of polar residues. So what is written here, or what is shown here, is the negative charge amino acid. So amino acid that can form a negative charge, and the amino acid that can form a positive charge. So those are the only amino acids that can form charges. Okay, a natural amino acid. So we are not going to talk about the unnatural amino acids or the cofactors that might influence the enzyme. So because we are just focusing on the structure of the enzyme, so these two categories are the main interaction that forms the opposite charge on the enzyme. Okay, of course, again depending on the pH. So they are chemical sensitive and ionic sensitive or chemical, okay, because it's a polar. So a polar, when you change the pH or you change the ionic concentration, so you can change the protonation of this amino acid. As you can see, you have a carboxyl function group or carboxylate shown here for 2 of the amino acids. So of course this will be deprotonated at a higher pH, okay. And if you look at on the left hand side, you have all these amines group where it can be protonated at a lower pH. Okay, so you know that when you change the pH, you can definitely change the protonation state of these 5 amino acids. Then theoretically you're gonna change like the whole structure of the protein. Okay, other than ionic interaction, you do have hydrogen bonding. Again, hydrogen bonding is the major component of a secondary structure, okay, because alpha helices and beta sheet are just formed by ionic bonding. We're going to look at it in more detail afterwards. And we also have dipole-dipole interaction, okay, so whereby the polar uncharged amino acid. So previously on number 1, this one is more charged amino acid, okay, but number 3, polar-polar interaction, is more for the polar but uncharged amino acid. So as you see, hopefully you can see the structure of the amino acid on the right hand side. If you can't see it, then by all means you just Google amino acid sequence, go to the image tab, and definitely you will get this table. So it's a general table, or simply just go to Wikipedia, Google amino acid, then you will see this table. Okay, so if you look at this table, alright, what we have here are all the purple ones, okay, the purple ones, amino acid with hydroxyl groups or amide-like group, okay. So of course you all know that these are polar, okay. Why it's polar or have a dipole? You need to go back to first year chemistry if you don't remember. If you do remember, then that's good, okay. Next we have van der Waals or London diffusion force that comes from a more induced dipole or temporary. So you'll have like an alkyl chain like that, okay. It's an alkyl chain where it can be induced dipole, where the electron is not static, electrons keep on moving, so you can have an induced dipole, especially if these amino acid sequences are adjacent to a more polar amino acid or a metal cofactor, for example, okay. So you can induce a polar, and this polarity is the interaction between this polarity, if you recall, okay, when you write down a delta minus and delta plus, so these are the attraction, the London diffusion force or the van der Waals interaction between 2 amino acids, okay. So it also generates a more hydrophobic, so that what we call as hydrophobic effects, okay. So it's it's basically, you know, a straightforward thing. It's interaction between non-polar amino acids. So these are what we call as hydrophobic effect. And again, remember that these are all temporary, so that's why when you introduce energy like heat or chemical changes, these bonds are easily broken down, okay. Alright, so a little bit more detail on the hydrophobic effect. So when we were talking about hydrophobic effect, in a bit more detail, it is not significant. So you can have hydrophobic effect between molecules, different molecules, for example. But when we are talking about hydrophobic effect here, is not significant for intersubstrate or interprotein. So when we have substrate, okay, and one enzyme or protein, okay, and of course in the biological system or in a chemical reaction, you don't use just a single enzyme, and you don't use just a single substrate. So you have millions and millions of substrate and enzymes in one beaker or in one test tube. Okay, so when we are talking about the hydrophobic effect, we are not talking about the interaction between those two. Okay, so there are interaction between the substrate, between substrates and between the enzymes, but these are not significant. I mean, they do play a big role. Of course, you cannot say that it's not significant at all, but they are not significant as in not the major factor that influences the catalytic process. Okay, so they are not the driving forces that we are talking about. Okay, and they are also not really, okay, about the molecule to water interaction. Okay, there is, but they aren't the major ones. Okay, so if, say for example, I ask you what are the driving forces influence in enzyme structure or biocatalysis, if you write down in the substrate or molecule water hydrophobic effect, it is still an acceptable answer. But if I ask you very specific, like what are the major driving forces in hydrophobic effect, and when you write down inter substrate or inter-protein interaction, then the answer is not acceptable. Okay, so depending on the question that will be asked, the answer can be a yes or a no. Okay, because again, what I'm doing here is I'm teaching you guys the basic component. Towards the end of the day, the more you read, the more you understand about the principle, and something like this, you cannot say that it's not there. Okay, it's not significant, but it is still there. Okay, so the hydrophobic effect is primarily involved in a protein substrate interaction, especially when we are talking about the interaction when it's already forming the enzyme substrate complex. So we're not talking about when it's floating around freely in the water. It's not that one. So we are talking about when it already forms the enzyme substrate complex, then it is very, very significant. Okay, the hydrophobic effect between those two molecules are very significant, as you will probably see next week. Okay, and also the hydrogen bonding between water molecules. Okay, when we talk about not significant between molecules and the water itself, because water is very tiny compared to a molecule. Okay, so but when we're talking about the interaction between molecules, millions of molecules of water, the structural water molecules, then it makes more significant. Okay, I was thinking about something else, but now I can't remember. Anyhow, okay, so that's basically when we're talking about hydrophobic effect, those are the things that you need to take into consideration and remember. Alright, again, to highlight, hydrophobic effect is not a cohesive interaction. Cohesive meaning the same molecule interaction, but as a result of disturbance of water interaction. So you have hydrophobic effect, and then water molecule comes in, and water molecule likes to be in hydrogen bonding formation. So hydrophobic effect is now influenced by water. Okay, this is an example of a hydrophobic effect, okay, of an enzyme. I'm hoping that the structure is a bit clear for you guys to see. Okay, so these are just an example of two different enzymes. So you have enzyme 1 and enzyme 2. So what it says here is that the major requirement for substrate type 1, so this one is scheme 2.20. if you want to go and see the book, okay, if you want to look at the book to look at the substrate type, I'm not going to touch about the types of substrate, but if you are interested to look at it, then by all means go to the book, to the book references. Okay, it says the major requirement for substrate type 1 to be selectively hydrolyzed by a protease such as alpha-chymotrypsin, the top enzyme, pepsin or papain, or subtilisin are the presence of a polar and hydrophobic group in the alpha center of R1 and R2 respectively, to mimic the natural substance amino acids. So enzymes, papain, pepsin, for example, are enzymes that digest polypeptides. Okay, but over here, what you can see is the hydrophobic interaction from the CBZ group. Okay, so this CBZ group is a bit bulky, almost like an alpha phenylalanine. Okay, so you can actually now use additional or a different substrate for this enzyme to actually work. Okay, so as shown here is alpha chymotrypsin and papain, and the specificity of these enzymes supposedly, some sequence of amino acid. But now when you have a substitute unnatural substrate, it can still forms or catalyze the reaction based on its specificity. Like for example, alpha chymotrypsin hydrolyzes the ester at the alpha position, while papain hydrolyzes the enzyme at alpha beta at the gamma position. Okay, so gamma delta, gamma. Okay, so an example of the hydrophobic effect, okay, just because of having the CBZ group. So without the CBZ group, it will not work. Alright, so it should come out earlier. Hydrophobic effect. Okay, so now we're gonna look at the first one is hydrophobic effect in a little bit more detail. The second one we'll look at the driving forces, which is a pH dependent enzyme function. Okay, so as I mentioned, enzyme function at a specific pH based on the amino acid sequences. Alright, so the carboxylic acid and the amine groups, the amino groups, not amino acid groups. So the amino groups in an enzyme makes a structure sensitive to a pH, as shown, if you recall, on the table of polar amino acids. So the presence of weak amino acid and bases results in the formation of a pH buffer. So if you recall, a buffer system, you need to use a weak acid and a weak base. So if you use, for example, hydrochloric acid, which is a very strong base, it does not work as a pH buffer because it dissociates 100% into hydroxyl ion and a chloride ion. Okay, but if you have a weak carboxylic acid, a weak acid like carboxylic acid, then you can then of course you can have a partial in equilibrium dissociation of the proton ion from the carboxylic acid. Okay, so this is basic chemistry. And when we're talking about buffer, outside of the buffer range, the pH system, the structure of protein will be affected. Okay, so there are certain limits, but outside on the extreme ends, not to say extreme ends mean pH 2, pH 1, okay, because it depends on the enzyme. So some enzymes can work in the extreme ends, but generally speaking, an enzyme works at a certain pH only. On the extreme ends, whether it's too acidic or too basic, the structural integrity can be dissolved, okay, and becomes denatured. And this effect, the denaturation process of I keep on talking about it but I didn't write it down. Denaturation. Okay, so this is the terminology when we're talking about a structural change of an enzyme from a natural state to a unnatural state. So denaturation. So the effect of the denaturation effect can be either a permanent ones or reversible ones. Okay, so reversible means that it deforms, but then when you change the pH again, it folds on itself, forming the original structure. Permanent ones can also happen, whereby you might have a lot of cysteine disulfide bonds. Okay, in extreme ends, the disulfide bonds might break, and then when reforming the disulfide bonds, it might not match up. Okay, imagine in a big protein where you have a a minimum of 1 disulfide bonds, you might have like 3, 4, 5, 6, or probably even more disulfide bonds. So 6 disulfide bonds, meaning that there are 12 cysteines. So 12 cysteines, imagine 2 to the power of 12 combinations. Okay, so there are so many combinations that can happen, or probably 12 to the power of 2. Okay, but I do have you do get my point, whereby a denaturation of dicysteines can can cause a permanent damage to your enzyme. Okay, not just cysteines. If you have a polar interactions, so imagine if it's just one polar interaction, it's very easy to actually reform the polar interaction. But if you have thousands or millions of polar interaction, and then you denature the protein from a tertiary structure back to a primary structure where it's just a single polypeptide form, to ask the protein to refold to its original position is very difficult. It's based on theory of formation, but we're not gonna touch about it. Okay, so an example. So when you talk about the example I've already mentioned. So again, this is just to show you the activity and the influence of change of pH. What will happen is that say for example the enzyme works at pH of 7. Okay, so if the enzyme works at pH 7, let us take a real life example, amylase. Okay, we have amylase in our mouth, in our saliva, so we have amylase. So amylase breaks down carbohydrate. Okay, so it breaks down the OH bonds, or the O bond, the glycosidic bond in carbohydrates. So it normally works at slightly lower than 7, but we're just gonna say in the middle one, 7. Amylase, if I'm not mistaken, is about 7.7 or 8 pH. Okay, so if you consider in the middle, there is the sweet spot, is the optimal condition for the enzyme. Okay, so of course the activity is at maximum. Okay, max activity. So over here we are not gonna we are not talking about the maximum velocity. So when you look at, if you remember the Michaelis-Menten equation, it's more Vmax. Okay, Vmax is maximum activity, but it's a rate. So when we talk about Vmax, it's a rate over time, the maximum activity over time. But over here we're just gonna say like the activity, the general terminology, activity of the enzyme. So maximum activity is at the optimal pH condition. If you go to a higher pH, what will happen is that the activity will gradually go down until at one point the activity might be 0, because the enzyme now started to denature. So a denatured enzyme will have no activity at all. Okay, my curve is a bit off. Okay, and then when you go to the lower pH, to the other extreme end, the same thing will happen. Okay, so the activity will go low and low, and towards the end of the day it will die off. Okay, and if you look at the shape, I'm trying to draw as best as I can. Okay, when we're talking about the shape of the enzyme, it's actually it's kind of like a bell shape. Well, it is a bell shape. Okay, that's what we call it, a bell shape enzyme. Okay, bell shape enzymatic activity. Okay, so that is the influence of pH. So it's a bell shape. It doesn't mean that. Why does it is a bell shape? If you recall, buffer. Okay, so enzyme is a buffer. A buffer works at a certain pH. So this is what it looks like. If you go back into your first lecture about a weak acid and base, or a buffer principle, this is how it will look like. It will look like a buffer, a bell curve shape. Okay, so same thing. The activity of an enzyme will have the shape of a bell. Okay, it's not straight. It's not linear. It's not skewed and whatnot. All right. So it's a matter of where you shift the pH. So if you shift the pH into 2, it's the same thing. Okay, so the activity will be a bell shape, like that. And if you move, if you choose an enzyme which is more basic in nature, the structure is also like that. Okay, so it's always trying to keep the bell-shaped structure. Alright, similarly for a temperature dependent enzyme function at specific temperature, and of course it's organism specific. As I mentioned, for human, for example, the optimal temperature is 37 degrees Celsius. So as you go down, or if you have a fever, it will go down. But in this case, alright, so if you look at this structure in the first place, alright, so if say the optimal one is 7, so it might still work at 9. Okay, at 9, normally enzymes at +2 or +2 or -2, normally enzymes still have its catalytic activity. It might not be as full or maximum activity, but it still have its own catalytic activity. Okay, and when you're talking about pH, a log of 2 is 100-fold. Okay, remember that, 100-fold increase in the pH concentration, the hydronium concentration, or a decrease, 100-fold decrease in hydronium concentration, the enzyme still works. But when we're talking about temperature dependent, an enzyme that works at 37 degrees, when it reaches say 41 degrees, okay, this is just a difference of 4, okay, 4 degrees compared to a pH which is 100-fold. So the enzyme activity is almost 0. So that's why when we have a fever, 38 degrees, so if a normal temperature is 37, 38 is considered fever, 39 straight away people will say, oh, it's high fever, and 40 is an alarming temperature, whereby normally if you have a high fever, you go to the hospital straight away, okay, because it's a very high fever. And at 41 or 42 degrees Celsius, most enzyme will die out. Okay, I'm not going to say all, most of it will die out. Definitely there are some that is already kaput. Okay, it doesn't really work anymore at 41 or 42 degrees. So that's why when we have a fever, our body tends to increase the temperature to not with the idea of not stopping our own body from working, but it's more on to deactivate enzymes from bacteria, viruses, and so on and so forth. Okay, so now you probably understand, if you have not understand previously, why we have a fever. Okay, we have a fever because our body wants to denature the enzymes that are helping the invaders, the bacteria, the viruses, and so on. Okay, and similarly, if you go down, alright, it will go something like that. So it's okay for the temperature to go down, but it's not okay for the temperature to go up. Okay, so it's a bit skewed in terms of temperature, but it still looks like a bell shape. So if I ask you guys about this and then you say it's a bell shape, it's fine, totally understandable. But yes, normally enzymes, if you lower the temperature, it still works, but if you increase the temperature, it will dies out. Okay, again, this is an example for human. For a bacterial enzyme, or for the organisms that lives in the floor bed, it might have a different temperature, or what do you call it, curve. Okay, temperature curve. Okay, I think that's it for today. It's already 44 minutes. So next week we gonna okay, so next week on the next week is on the 18th. We gonna look at the driving forces on the structures. Okay, in the primary structure there's none, secondary structure, tertiary structure, and quaternary structure, and how these forces influences the structural integrity of an enzyme. Alright, so finally, the references, if you again want to find the books that I'm using, so these are number 1 and number 2. Number 3 is all the PDB-ID, the structure of the proteins, if you are interested in looking at the structure of the enzyme. And finally, additional reading. So there's 3, 1, 2, and 3. Okay, so these are actually some of the images that I actually use in throughout the lecture materials. Okay, I think that's it. Thank you, and see you guys next week. Peace out.